So good morning, everyone. Just as Avishai and everyone else, I'd like to welcome you to this event. And just like everyone, I'm sorry that we're meeting in person. Actually, I'm sitting in front of my laptop, so I don't even see any of your faces. I just see my presentation. I'll tell you a little bit about condensed matter theory. Weizmann Shahal will tell you more about the experiments. My guess is both of us, and like everyone else, we're going to try to explain to you how wonderful Weizmann is. I'm not I'm not trying to conceal this. So in condensed matter physics, the fundamentals of the field are that we think we know who are the characters of the field. We know condensed matter system is made of electrons and nuclei. We think we know the rules by which they operate, which are quantum mechanics and electromagnetism. So it seems as if we know everything. But in fact, we don't, because what we see that we can build systems and we can control parameters. Like, we can build three-dimensional systems, two-dimensional, one-dimensional. We can control the temperature, the magnetic field, the electronic density, whatever you want. And what we find is a breathtaking richness of phenomena. I'll give you, the tip of the iceberg. I'll show you very few examples. But the field is amazingly rich. And what we see more and more as time goes by is the huge effect that the interaction between all these constituents has on the behavior. Now, this is the first example. You see, this is an experimental, this is a picture of an experimental system. It's a piece of a semiconductor. There's nothing, particular in this. It's made of a material called gallium arsenide, but you can reproduce it in about 15 other materials. And just, you push a current and you measure voltage. And this is what you see. It's called the quantum Hall effect. You look at the resistance when you push a current in this direction, and the sample is subjected to a magnetic field perpendicular to the sample, and it's two-dimensional. What you see that the whole resistivity, this red line, shows these steps, these plateaus, which are precise to about 1 part to 10 to the power 10. It's one of the most precise phenomena in physics. Moreover, if you look at the longitudinal resistivity, you see these peaks. Going from here, where you're at the minimum, to here takes you a change of a few percent in the magnetic field that you apply. And what you see is a variation of 15 orders of magnitude in the resistivity. So there's something extremely sensitive in this system. And it's made of electrons and nuclei, which interact by Coulomb interaction and Schrödinger equation. How can they make something so dramatic? Here's another example, much more recent, actually from a couple of years ago. This is a system where people take two monatomic layers of carbon called graphene, and take two layers of graphene and rotate them with respect to one another and then glue them. So put them one on top of the other with a slight rotation. What you see again is what you see here is the resistivity as a function of density. And you see these changes. Look at the scale here. Changes of orders of magnitude. Here you see 5 orders of magnitude, but it's even more because you see the peaks continue to go. As you change a parameter, in this case the electronic density, by a couple of percent. So there's something, these electrons are able to produce a behavior that's extremely sensitive to parameters. So these are just 2 examples. Now what I'd like to do is to tell you what I call the life cycle of a condensed matter theory. I'll tell you the general principle and then I'll give you an example. So the life cycle starts usually with the observation of some phenomenon. Excuse me. When a phenomenon like the quantum Hall effect that I showed, like this twisted bilayer graphene that I showed, like many others, when it's discovered, the first thing is to try to formulate some set of new rules. You try to explain the phenomena that you see. But you don't stop at that. Once you have the rules, you try to explore the possibilities that those rules open to you. You try to see what are they telling you, what other phenomena you can predict from these rules. what consequences will be to the phenomenon you look at, and so on. And then comes what I think is the most exciting part of theoretical work, which is you try to break your own rules. You're trying to find situations where the rules don't apply, and then you look at those situations trying to predict new phenomena. So that's the way it goes. You formulate rules, you see what they're telling you, and then you try to break them. And I'll give you an example. It's an example that spans a century, but it's a very beautiful one. Sometime in the first half of the 20th century, people understood, and not people, I mean, Fermi, Dirac, Bose, and Einstein, understood the notion of quantum statistics. They understood that there are two types of particles in the world, bosons and fermions, only two types, bosons and fermions. Bosons don't get any change to the wave function when you interchange two particles. Fermions get a minus sign. That's a set of rules. Do they have consequences? Oh boy, they have a lot. Fermions, this minus sign that they get when you interchange a position of two particles, that's the source of the Pauli principle, which basically explains all of chemistry. Not only that, this fermionic statistics explains also why metals behave as metals. And the absence of this minus sign explains why bosons behave as they do. Superfluidity, superconductivity, light, sound, all these come out of the fact that you don't get a minus sign when you interchange two particles. Then you ask yourself, can I break these rules? That's present day research. We now understand that you can. That it's not that you have only fermions and bosons. That the founding fathers were not right. That in two dimensions, and if there are the proper interactions between electrons, you can get a new type of quantum statistics, which are called anyons. For anything is possible, not just fermions and bosons. So now that we understand that we can break these rules this way, we formulate a new set of rules. We try to understand what is the statistics of anyons. And we now understand that when you interchange two anyons, the wave function gets an arbitrary phase, not just minus or plus. We now understand that this leads to something called topologically protected ground state degeneracy, which is a ground state that's degenerate in energy, several ground states that are degenerate in energy, and this is a degeneracy that does not require symmetry or any special circumstances. It's generic to certain systems. We understand this notion of symmetry protected topological states, which are states where this very exciting behavior happens only under certain conditions. So sometimes, as I said, you have topologically protected ground state degeneracy, which does not require any symmetry, and in some other cases it does. We understand all of this. Then we ask ourselves, what are the possibilities that this set of rules open? First of all, can we see this in experiments? And actually last year, or in the last 2 years, there were a couple of experiments where anionic statistics was really probed to its deep core. Not only that, we have this hope and this vision of using this anionic statistics, in particular a special type called non-abelian anyons, as quantum bits for quantum computation. So that's how we explore. And last, we want to break the rules or to expand them. And now we know how to break the rules that I told you about anyons. We know that we can take them out of 2 dimensions. We know that we can even have some version of them realized without strong interactions. For example, in quantum wires and in Johnson junction, those are called the Majorana zero modes. There are some version of these non-abelian anyons. So this is how the story goes on. Yeah?
1 minute.
Okay, good. The last thing I want to say is something about condensed matter at Weizmann. So I told you, the characters of the play are known. Those are the people. This is only the theory. So the characters are known. The key is the interaction. And here's another set of pictures of the same guys. And the key are the interactions. And you see that's the interactions between people in the department. I think that one thing that makes our department particularly strong is this rich network of interactions. We talk all the time to one another. Whenever an experimentalist has a new observation, they come to us. Whenever we have a new prediction, we go to them. It's one of the most strongly interacting places I've seen in the world. Now, another thing which I think is very much of an interest to you guys, to prospective students, is what happens after you study at Weizmann. So I gave you here a few examples of people who graduated from our department from the theoretical side in the last few years. And you see a CTO in a very exciting startup, a professor at Tel Aviv, a professor at the Technion, a quantum computing company guy, a professor at Columbia, a postdoc at ETH, someone who works for Amazon and now comes back as a professor to the Hebrew University. The quality of education that we give to our students is tested every time by what they do next. And they go to postdocs at Harvard, MIT, Caltech, Stanford, Berkeley, all the great places in the world, and they continue then to industry, to faculty positions, to great places. So to summarize, I think that our strong points are the research is state of the art. The atmosphere is of extremely strong interactions between everyone to everyone. Sometimes I stay home just because I need a few hours when no one talks to me. I'm a theorist, experimentalist, students, postdocs, faculty. The interaction between theorists and experimentalists is particularly strong. And last, there's also a very strong interaction with the global community, as you saw in the list of places that our students go to. So I'll stop here and I'll thank you for listening. And if there are questions, I don't know if you will run this one.
Thanks very much, Ady. I think we should move to Shahal, and if we have time by the end of Shahal's part, then we can have questions to both of you.
Okay.
Hello, everyone. Nice to have you this morning. My name is Shahal Ilani, and I'm going to give you a bit of a flavor of what does it mean to do experiments in condensed matter physics in Weizmann. So in condensed matter physics, we are interested in what electrons, typically we're interested in what electrons do in material. And you know that you have electrons in your phones and your computers, and if you open them up and you look very closely, you can see that all the functionalities of these devices is based on the fact that the different materials, electrons can do different behaviors. They can be insulators, they can be metal, semiconductors, and this is enough to create all the electronics that you know. But in fact, this is really a small part of what electrons can do. And there are interesting features of electrons that today's electronics do not use. And there are two tricks that are relevant. One of them is that electrons also obey the rules of quantum mechanics, which can do very bizarre things. And the other one is that electrons try to stay apart from each other. They repel each other. And these two properties, if you put them together, they are trying to pull to different places of the physics. Quantum mechanics want to make electrons behave like waves, and interaction want them to avoid each other, meaning that they want them to behave as independent particles. And if you put these two things together in the right amount in a system, the system has to find some interesting compromise between them, and a lot of the interesting behaviors that we know in condensed matter physics come from the compromise between these two properties. And what we're actually interested in is to find what kind of new states of matter, new behaviors can electron do when you put these ingredients in. So you know that atoms have different states of matter, gas, liquid, solids, and this gives a lot of the richness that we have in our world of actual materials. In fact, electrons can have by themselves phases of matter, The fact is that if you look on all the electronics and what kind of phases of matters that we use today practically, they're only relying on the gas phase of matter of electrons. They're relying on electrons being a non-interacting particle. But if you put interactions inside, you can start getting much more interesting collective phases. You can imagine that electrons maybe have liquid phases, solid phases, the equivalent of atoms. And in fact, long ago in condensed matter physics, people discovered a superliquid phase, which is a superconductor in which electrons do something very bizarre. They couple in pairs and move together through the materials like pairs dancing on a ball floor. But there are many other phases that were predicted, like the solid phase and liquid phase, predicted many, many decades ago. And it's not easy to find them. In fact, in the search for them, people found very other interesting phases, like the fractional quantum Hall effect that was awarded the Nobel Prize. But these phases remain still mysterious. And these are the kind of things that we are trying, these are an equivalent are the things that we are trying to find in condensed matter physics. So why is it hard to find these phases experimentally? Well, what you want is to look on a solid and actually understand what the electrons inside the solid are doing. For example, whether they create a quantum solid of electron within the atomic solid. So they are hidden inside, and the question is, how can you tell what they are doing? So you can imagine doing some simple experiment like measuring the current, measuring the heat conductivity, measuring response to optics, but this is very hard to, from these kind of experiment to deduce what is the actual structure, what are the phases that electron take. And in fact, one interesting approach is to take pictures of electron, use probes that can scan and image the electrons in space. And in Weizmann, in our department, one of the strongest things that we have is that we are one of the strongest departments in the world in scanning probes that image various aspects of electronic phases. I'll give you an example from my lab, where what we do is we image the electric field that these electron produces using a very, very sensitive detector that can sense 10 to the -1 newtons, which makes it very easy for it to see even the field of an individual electrons. And when you scan it across a sample, you basically get pictures of how electrons are organized in space. So how does an experiment like this looks? It starts from a very large lab that is one of the quietest places in Earth because we want to look on small things and not vibrate. Then inside these labs, we have typically fridges that can take the physics into very low temperature, very close to the absolute zero, because we are interested in phenomena that are quantum and we don't want to disturb it. At these low temperatures, we have scanning motors that can move things on the resolution of individual atoms. And at the edge of all this, we have interesting detectors. In my lab, it would be the world's most sensitive charge detector. And you cannot visit it physically, unfortunately, but I just want to tell you that in principle, you can take a virtual tour. Here, you can look on the webpage and you can see how a lab in Weizmann looks. You can go through a lab in detail, see what we do, how the instrument, what is the level of experiments and infrastructure that you will find when you come to Weizmann. So the last thing I want to mention is what kind of physics we can do with these experiments. So what we can do is we can actually see new phases that electrons possess. Two new phases that we succeeded to see directly are the quantum crystal of electrons and the fact that electrons can behave as a collective liquid and break a lot of the rules that people think that electrons have. We are also looking on system that Ady mentioned, and in the department we are looking on, many of the researchers are looking on two-dimensional atomic layers of materials, for example, graphene, or layers of twisted graphene. Sounds like very simple systems, but in this simple systems, people find almost all the physics, all the interesting physics, collective physics of condensed matter that you learned and you will learn in the next 10 years. So here you see two examples of two new phases that my lab discovered in these materials. And finally, we are also interested on whether we can change completely the rules for electrons. So for example, we know that electrons repel each other, but can we make electrons attract each other? And in fact, you can one can see that you can make electrons attract each other via their repulsion. So these are basic rules that you learn in undergrad about what electrons do. But if we have enough controls and a good measurement system, we can even change the basic rules that electrons are obeying, and with this discovering interesting physics in the solid state.